Okay. The plan for today, pretty straightforward. Just discuss section 8.3, continue on with applications, discussing moments and centers of mass. I'm having a bit of an allergy bad day this morning and afternoon. So if I have to mute myself for a second, I apologize in advance. The quote of the day today is from the composer Hans Zimmer, who composes scores um, for big movie productions. Probably up there on the scale of somebody like John Williams. I think John Williams is, he's only at the level of John Williams, but you know, Hans Zimmer is a pretty famous composer. And a quote that I was watching an interview with him, and a quote that he said, something he said really stuck out to me. The reporter asked him something along the lines of like, how would you describe your music? How would you describe your music to somebody who hasn't heard it before, something like that? And his answer uh, was this: at my best, words will fail you because I'm using my own language. And I think this really gets at the heart of uh, the aesthetic humanities, so like uh, painting or drawing, things like poetry, even. I mean, poetry uses our language, I suppose, but it uses it in a unique way. Music, these kind of abstract forms, they express something that can't really easily or maybe not at all be expressed using words. So that there's a sense in which they explore ideas that are kind of so much at the frontier of our thinking that we haven't even found ways to really put those ideas into words yet. And that's what they're exploring. So I think that's an interesting way to approach this. And it always kind of irks me, the idea of like a book report or a book summary or something. And don't get me wrong, like I read book summaries. I'm like, yeah, if I'm looking at a book, I want to know more about what it's about than the uh just the title of it. Um but to say something like, well, write me a book report and in 2 paragraphs explain what this book was about. It's like, well, if you could really explain what a book was about in a couple of paragraphs, and it took the author 600 pages to write the book, um, either the author did a terrible job or you didn't really get the book or something. I don't know. Like, it's there's this idea that a good book resists summarization. And I think that's kind of what he's saying here, is that in a sense, like, if I could explain to you in words what my music is like, then my music would just be silly, right? I would just say, oh, it's like Mozart. Well, then you're just copying off of Mozart, right? So that I think that's what he is really saying here, is when he's really being unique and creative, his music is unlike anybody else's. And I think that's in a sense the point of art. Okay, so that's the thought for today from Hans Zimmer. So moving on to 8.3, moments and centers of mass. We're going to kind of build this up. We're going to start with a 1D discrete case, move to a 2D discrete case, generalizing a little bit, and then move to the 2D continuous case, which is where we'll kind of stop in Calc 2. And in Calc 3, we'll even go a little further. So looking at maybe a 3D continuous case, or a case where the density, as we see down here, maybe is not constant. So this is something that, I know a lot of you are going into fields that require physics background. And so a lot of you have probably seen some of this before. But hopefully this point of view will either maybe give you a new perspective or flesh out some of the details, um, or maybe even introduce you to something that you haven't really seen before for some of you. Okay, so let's start with the 1D discrete case. And we'll also start with just 2 masses. Consider 2 masses, M1 and M2, at locations X1 and X2. And let me bring up my notes here so I can draw my pictures properly. So let me draw a little picture here. We're going to assume these masses are sitting on a weightless bar. So this black line is a bar, it's weightless, or massless, or however you want to say it. And I have this mass of size M2, It's located at position x2, and I have some other mass, M1, at position x1 on the bar. And these could be different masses, of course, right? Not necessarily the same mass, but we're thinking of them as being all localized exactly at that point. So it's not like a smear of mass or like a brick or something that's kind of spread out over some distance, but it's all localized right at that one point, x1 or x2. And really kind of our goal in finding a center of mass, which is really our end goal here, is to ask ourselves, maybe mass 2 is quite a bit heavier than, or more massive than mass 1. And I want to ask myself, okay, if I have a fulcrum, a little triangular doodad that the thing could maybe balance on, where should I position that left to right so that mass 1, which is kind of wanting to make the system rotate counterclockwise to the left, and mass 2, which is kind of wanting to make the system rotate clockwise to the right, so those tendencies perfectly offset and the thing balances. It just sits there and doesn't move, doesn't fall off to the left or the right. Where should that be? Well, that should be at a location, and I'm going to write the location on top for this one. Sorry about that. I have the triangle on the bottom, but that'll be at a location we'll call X bar, the center of mass. Again, remember, we're assuming the rod is weightless, the black rod, so we only have kind of the influence of mass 1 and mass 2 to worry about. And remember that we have mass 1 is kind of to the left over here. So mass 1 is tending to impart a rotation in this counterclockwise direction to the left. Like if I, got rid of mass 2 altogether and just let the system go, the rod would rotate counterclockwise towards mass 1. And similarly, mass 2 is wanting to make us rotate clockwise to the right. If we got rid of mass 1, the whole thing would collapse to the right side. And I'm going to be imprecise here. I'm, probably going to annoy some physics professors, but roughly speaking, the moment, when we talk about the moment about a point, due to a certain mass at a certain location, what we mean is, roughly speaking, the kind of impetus for rotation. So this mass m1 at position x1 relative to the point x bar, say that's off to the right, tends to impart a rotation that's counterclockwise. And it tends to do that with a certain, let's just call it something like strength or a certain magnitude. Maybe it just wants it to rotate counterclockwise a little bit. Maybe it's just a little bit of mass and it's kind of close to X bar. Or maybe it's a lot of mass and it's far away from X bar and it wants to rotate it counterclockwise a whole bunch. So there's a direction that it wants to rotate things and a strength of that direction, a magnitude. So that's the moment. And likewise, from M2, there's also a moment imparted by M2, an impetus from the mass M2 to rotate in the clockwise direction. And these moments are simply the product of, I've run out of colors here. Maybe I'll use red again. They're the product of the mass with the distance that the mass is from the point under consideration. So if we're looking at the moment about x equals k, here we're using x bar for k. But moment 1 would be m1 absolute k minus x1, and m2 moment 2 would be mass 2 times absolute k minus x2. Now, like above, let's suppose that k is between x1 and x2. Then that means the k is bigger than x1 and k is less than x2, so we can get our signs resolved from the absolute values and get rid of the absolute values. And as I have kind of outlined above, we want to choose this k, or our goal here is to choose this k, maybe not in general, but our goal here is to choose the k so that the moments cancel, so that m1 equals m2. We call this value of k the center of mass. We denote it by x bar. And setting m1 equal m2 with a little bit of work gives us this equation that, or this formula that I suppose you probably recognize from intro physics class, or maybe even from high school. If you don't recognize it, no big deal. But it's m1 times x1 plus m2 times x2 over m1 plus m2. Or really, what I actually see, what is m1 x1? That's just the moment due to mass 1 at position x1. Well, what is m1 x1? That would be when k equals 0. And what is m2 x2? Well, again, that would be the moment due to mass 2 at position x2 when k equals 0. This is just kind of the overall moment about 0. And then what is, if I can select just the denominator here, which I am struggling to do, what is the denominator? It's m1 plus m2. Well, that's just kind of that's just the total mass of the system, right? M1 plus m2 is just all the mass that we have. So x bar is like the ratio of the overall moment to the overall mass, right? So the center of mass in this case is the ratio of the overall moment to the overall mass, or we could actually generalize this to n masses at n locations, and x bar is going to be sum of mi(xi) over some mi. Okay, so we have a result for the 1D discrete case where we have discrete masses, certain m1, m2, m3, etc., at discrete points where all of the mass is located at, or all of the mass of m1 is located exactly at x1, all the mass for m2 located exactly at x2, and so on. And this would be the balance point. This is x bar is where we should put our little support so that all of the different moments, some wanting to make it rotate clockwise, some counterclockwise, all kind of cancel out. Why do we care about the center of mass? Well, one application of the center of mass is that in a lot of physics applications, certainly not all of them, but in a lot of them, we have some big complicated system, some big, thing with a whole bunch of atoms and a whole bunch of interactions and all of that. Very complicated to model, but often we can treat this whole system, this whole complicated system, as though it was a single particle with mass m located at x bar. And we can resolve our forces or whatever we need to resolve, just basically taking this complicated object, a car or something like that, and pretending it was just a point mass moving in some way, or a billiard ball or something like that hitting another billiard ball. There's all kinds of atoms and molecules and friction and all kind of things, but maybe you can get away with just modeling it like one point mass colliding with another one, and when they collide, which direction are the forces going to resolve, which way they're going to end up going. And that's probably going to be a pretty accurate approximation in a system like that. Another, I think, good example is consider the Earth. For our purposes, we'll assume the Earth is round. If you would prefer the Earth to be flat, you can work that out on your own. But we have the Earth, three-dimensional globe, and person standing on it, which I've of course drawn much larger than to scale. And kind of in some sense, every atom or every subatomic particle or whatever in the Earth is, maybe I'll draw them this way, is like attracting every subatomic particle from this person due to gravitational attraction, right? I mean, this is an unimaginable number of interactions. But how practically do we resolve these kinds of questions? Well, we say, I'll suppose the person is standing here and they have mass m1 at location x1, and the center of mass of the Earth is mass 2 at location x2. and I resolve the forces by just having those two centers of mass attract one another. This is kind of a reasonable thing to do because, if we think of all of these interactions, like there's going to be a particle. Was I drawing my particles in blue? There's going to be a particle over here from the Earth pulling on the person, but there's also one over here pulling on the person, and they kind of like the sideways pulls kind of cancel out. So this makes sense to do in this scenario, right? I'd much rather deal with just one center of mass of one person at one location, the center of mass of the Earth at another location, the line between them, just thinking of that as maybe one dimension, and I have maybe a gravitational interaction between those two masses, or maybe something else that I'm interested in. Okay, so let's bump up a dimension. So here we have the 2D discrete case. So again, let's consider two masses, M1 and M2. These are point masses located at a specific point, but here they are at two-dimensional locations, x1, y1, and x2, y2. Okay, let me again draw a picture. Did I make my masses up here? Were they green? Okay. Okay, so again, I have these two masses, uh, M1 at X1, Y1, and M2 at X2, Y2. So here I'm kind of imagining that this two-dimensional plane is like a massless plate, and these two masses are just sitting on this plate. I've drawn the origin here kind of for reference, the X and Y axes, but we're just thinking of this as like a massless plate, and two masses are sitting on that plate. So I almost have in a three-dimensional perspective, something that looks a little bit like this. Oh, and I want to know where to put my fulcrum so that the plate balances. Again, massless plate, but two point masses sitting here. Right? If M1 was very large and M2 was small, I would put my fulcrum kind of close to M1. Vice versa, I would put it close to M2. If they're kind of, about the same size, I'd put it maybe roughly in the middle, kind of where it is here. So now if I think about the forces or the moments or the kind of tendencies to create rotation from these two masses, well, I noticed that from M1, from its X position, there's a tendency to rotate this direction about the Y axis, right? Or over here, maybe in a three-dimensional kind of uh, diagram. Let me see, this would be the X axis and this would be the Y axis, I think, if I am doing that right, keeping it in a reasonable perspective. So we see that relative to the Y direction, the kind of bottom left to top right direction, M1 is to the like negative X side of where this fulcrum is positioned. It's going to tend to make the whole plate just M1 by itself want to rotate this direction. So kind of like if you took your right hand, pointed your thumb to the left, and then like curled your fingers around, the way your fingers are going is the way that that plate is going to want to rotate from the influence of M1. Note that that is due to the x coordinate of m1. The further x1 is to the left, the stronger this impetus for rotation in this direction is going to be. And the further that m1 is to the right, the less strong that impetus of rotation is going to be about the y-axis. So the tendency to rotate about y is due to the x distance to the x position. And then we have something similar for m2. M2 is going to impart a tendency to rotate the other direction. M2's influence is going to be to want to impart rotation this direction about, because it's kind of to the right of the fulcrum relative to the y-axis, or it's to the right of the y-axis. So it's going to want to make everything rotate the opposite direction. So I can balance the tendencies to rotate about the y-axis alone by choosing my x coordinate properly. Okay, so my is the moment about the y-axis. It's the tendency for the system to want to rotate about the y-axis, or about an axis kind of parallel to the y-axis. And as I mentioned, my, the moment about the y-axis, the tendency to rotate from this perspective kind of left to right, not up or down, my is related to the x positions of the masses. If m1 was located twice as far to the left, it would want to rotate to the left much more strongly, or m2 was located more to the right, it would want to rotate to the right more strongly. So my is the moment about the y-axis, tendency to rotate about the y-axis. It's related to the x positions of the masses. So my is the sum of mi xi. Note the difference in the variables there. My, the tendency to rotate about the y-axis, is going to look like the sum of the moments due to the x position, because the x positions are what's giving kind of the lever arm for rotating about the y-axis. Right? The x positions are what rotates us left to right, and that's about the y-axis. So a little bit, it seems like it's backwards when you first see it, but when you think about it, it makes sense. And then, of course, m, or sum of the masses, is just like it was before, just sum of mi. The total mass is just the sum of the masses, just like before. So if I want to balance the left-right tendency to rotate, the tendency to rotate about the y-axis, I have to decide where along the x-axis to position my fulcrum, to position my balance point. The x coordinates of the masses lead to tendencies to rotate about the y-axis. And to balance those tendencies, to balance those moments, I need to choose the x position of my center of mass. I need to choose the x position of my balance point. So x bar is related to my, which is related to the x's. So in the end, it kind of makes sense, right? That x bar is directly related to the xi's. That makes sense. But why do we sandwich in there the moment my related to the xi's and the x bar? Well, it's because the xi's cause a tendency to rotate about y, the y-axis, the moment about the y-axis. And we're trying to get rid of that tendency to rotate about the y-axis by choosing the x position of our balance point, our x bar. So hopefully that kind of clears things up a little bit. It seems very strange that x bar is my over m, which is some mi xi over mi, or some mi. But that's why that's where all of this relates to one another. And then, of course, we do just exactly the opposite in the other direction. I've used up all my colors now, but I see that for M2, for mass 2, or for mass 1, the y coordinate is going to cause a tendency to rotate about the x-axis. M2's tendency is going to be kind of in this direction, and M1's tendency to rotate about the x-axis is in that direction. So the y coordinates of the masses result in tendencies to rotate about the x-axis, right? The further up M2 was, or the further down M1 was, the stronger that tendency to rotate would be, and vice versa. So the y coordinates give tendency to rotate about the x-axis. The y coordinates are related to the moment about x. And to resolve those, to make them cancel out with a specific balance point, we choose a y location for our balance point. We call it y bar. So analogously, y bar equals the moment about the x-axis over the masses, which is some mi over some mi. So we do have this kind of like this intermediate step, or really intermediate nomenclature that seems a bit backwards, but it does make sense when you think about it. So, and these are the formulas for the 2D discrete center of mass. And again, this x bar, y bar, this will be the point. Maybe it's, maybe it's something like here. Maybe M1 is kind of more massive than M2. This would be the point where I would want to put my support beneath this plate to make the thing balance. So this would be, say, x bar, y bar. Same thing over here. If this was where it was balancing, I would call this x bar, y bar. So we see our 2D setup, our 2D formulas are really exactly the same as the 1D formula, just twice. And really the major complication is, where did I have it here? Up here, I just had kind of capital M over little m. So if I wanted to write x bar equals capital M over little m, to make it look like these down here, really the only confusion is which one goes with which one, right? Which label goes with which x bar or y bar and with which x or y coordinates. The x bar goes with the x coordinates. The y bar goes with the y coordinates. That makes sense. But the labels are just a little bit backwards because we're talking about the moment about the y-axis, the tendency to rotate about the y-axis, which is caused by the x positions and vice versa. Okay. Any questions on this? All right, so let's jump down now to the 2D continuous case. And this is going to be the case where we're really going to see the Calc 2 pop up. But we had to establish how the essentially algebraic side of things works, the discrete side of things works, before we generalize the continuous side of things. So here what we're looking at, kind of just diagrammatically, we're looking at, we have some kind of sheet metal or something like that. And my question is, oh, did that? I moved my pens in a funny order. There we go. And I want to ask, again, where should I place a support? That does not look like it's at the center of mass, but just bear with me, I suppose. Where should I place a support so that this balances? But here, I'm not saying that I have a mass here and a mass here. What I'm saying is that the sheet itself is the mass. I have an irregularly shaped chunk of sheet metal, and that itself is the mass, right? So I no longer have point masses. I have kind of a smear of mass across a 2D region, and I want to decide where to put the balance point under here. I want to decide what is x bar, y bar, what is essentially the center of mass. In this case, we call this a centroid, because I no longer really have discrete point masses. I have kind of a smear of mass across a region, and I'm trying to decide where the balance point is. Okay, so let's get a little away from a diagrammatic structure and a little more towards something that looks like a function that we can handle. So suppose that I have uh, a two-dimensional object going from x equals a to x equals b with a curvy side y equals f of x and with bottom at the x-axis. So this is the region. It has three flat sides, one curvy y equals f of x side. And I want to find the center of mass of this region. I'm going to assume constant density. So I'm assuming constant density here. So my sheet metal, it's not like thicker at one end and thinner at the other end, or it's not like made out of tungsten on one part and steel on the other part and like welded together or something. Constant density throughout. So uh, constant area density. So if I punched out a 1 square centimeter chunk punched through uh, this sheet, anywhere on the sheet, it would have the same mass, whatever, rho grams per square centimeter. So I'm going to call this density rho, the Greek letter rho. It looks a little bit like a P, but it's rho, the Greek letter. Relaxing this assumption is something that can be taken on in Calc 3. So what if we did have a sheet that varied in density, across it according uh, to some relation? Okay, so let me get rid of these. Can I just delete these? Yeah, let me get rid of these. And we kind of know the setup now. We have this like smear of mass from A to B, from the x-axis to y equals f of x, and we want to find the center of mass of it. I mean, just looking at it, it's probably like about here-ish or something. If I took a piece of sheet metal, cut this shape out of it, three flat sides. Let me make these look a little more like sides now. Three flat sides, and then one y equals f of x side, and I cut the shape out of it and try to balance it. I'd probably have to put the support something like at that green point to make it balance. Oh, okay. Now the question is, how do I find x bar and y bar? Well, let's start off by trying to find the moments. And here what I realize is that if I have, well, two-dimensional, there we go. If I have my two-dimensional discrete case, I know how to solve that. Okay, so let's take a look at this. As it is now, I'm not really sure what to do, but I might realize that if I use the same kind of, at this point, old Calc 2 trick, and I say, well, instead of taking the entire chunk from A to B, what if I take much smaller chunks? So imagine cutting this into lots of different slices of width delta x. Now, for demonstration purposes, I'm going to make a slice kind of big here. So we have a slice delta x, and maybe this is like the ith slice. I'm making it big just so we can actually see what's going on, but I would have more of these over here and more of these over here as well. And they would all be the same size delta x. They'd be pretty thin slices. Again, just making this bigger so we can see what's going on. Well, this is a slice that has width delta x and that has height. Well, the height is kind of approximately, let me do this in a different color, maybe green. The height is approximately, and maybe call it f of xi, some x coordinate in this ith interval, maybe the left endpoint, maybe the right endpoint, whatever. Right. So really what I have here for my ith chunk is a rectangle. Again, constant density rho. It has height f of xi and width delta x. Now there's something that I haven't mentioned so far, but I'm going to jump down a little bit here. So side note, if the region is symmetric about a line of symmetry, or maybe in the discrete case, if we say that like if our masses all lie along a certain line, and if rho shares the same symmetry, that really only applies in Calc 3 because here we're assuming rho is constant, so it has all of the symmetry that we might ask of it. Then the centroid must lie on that line. So if I can find a line of symmetry, the centroid has to lie on that line. In other words, I know that a rectangle is symmetric left to right about its left to right midpoint and same top to bottom. So I know that this point, what is it? It's going to be like x sub I plus delta x over 2 for the x coordinate, comma 1/2 f of xi for the y coordinate. But as delta x goes to 0, I mean, this kind of just goes away, right? So this midpoint of this rectangle is going to look like, whoop, one too far. It's going to look like xi, comma 1/2. That 1/2 is important. It's half the height is where this midpoint is, f of xi. I'm not doing the xi plus half delta x because, again, the delta x is going to be going to 0. That contribution is going to go away. Okay, so what is the mass going to be of this chunk? The mass, m sub I, well, it's going to be the area times the density. Well, that's going to be rho times, well, the area is simply f of xi delta x. Okay, what's the mass as a whole going to be then? The overall mass is approximately the sum of the masses from each of these little chunks, right? From this one and this one and this one and the one we're considering and all the ones after it. Rho f of xi delta x. And then we do our same trick as always. We let the number of intervals go to infinity and delta x go to 0. Our approximately equals becomes an equals. Our sum becomes an integral from a to b from our two endpoints here. Rho f of x, and our delta x becomes a dx. So we just found the mass of our entire irregular shape. That's the mass of this thing with the 3 flat sides and the curvy top side. So that's our formula for the mass. Or here I pop the rho out front, but rho is just a constant in this case, it can come out front. More generally, if rho was, say, a function of x or something, it would need to stay inside. Okay. So we got the mass, and I think we can see how we might want to get the moments now. I can say that this little rectangle here, this ith rectangle over here, on one hand, I can think of it as a smear of mass across this rectangular section. But on the other hand, remember the kind of magic of centers of mass is that we can take this rectangular smear of mass and basically treat it as though it was just just its mass located at its center of mass. So its influence on, say, the moment about the y-axis or the moment about the x-axis, that's the y-axis, of course, its influence on those moments is basically just going to be as though I had a point mass of little m, or sorry, little mi, located at this point, xi comma 1/2 f of xi. So really what I've done is I've reframed this problem. Oh, I've kind of reframed this as though I have a bunch of point masses, M1, M2, etc., at some different locations. That sounds a whole lot like the 2D discrete case. I know the location of the center of mass here. So let's look at, where should we start? Let's start with, all right, let's start with my, the moment about the y-axis. And then shuffle my papers around. Let's see. Okay, so there is my mass. I'll just kind of cordon that off. And then let's look at my, the moment about the y-axis. So this is the tendency to rotate about the y-axis caused by this smear of mass that's this roughly rectangle, or really this kind of point mass, mi, located at this point. But let me call this my subscript I, just to make it clear that we're only talking about the influence of this little piece here. But that moment is just like the amount of mass times the x coordinate. The tendency to rotate about y is related to the x distance, right? The further to the right we are, the stronger that tendency to rotate about the y-axis. But that's just, that moment is just mi times xi, or the sum of the contributions from all of these little delta x pieces is going to give me my, an approximation to that. That gives me mixi. And then here again, I want to look at what is the mass of this individual little rectangle. Well, mass, mi, is going to be f of xi times delta x. That's the area times density rho. And then I still have an xi to come down. So my mass is going to be the area of this rectangle, f of xi times delta x, times the density per unit area, rho. And then the xi product comes down just from the fact we're dealing with a moment here. So my is approximately, if I kind of rearrange things a little nicer, I get rho xi f of xi delta x. That's all, of course, inside the summation. Although I guess the delta x in the rho can come out, but we're thinking of it being inside the summation. And that's approximate. But then I do my usual trick. n goes to infinity, delta x goes to 0. My then, the approximate becomes equals. We get an integral from a to b. I have rho x f of x dx. So that's the moment about the y-axis from this entire two-dimensional sheet, this kind of smear of mass. That's my for the whole sheet that has three flat sides and top curvy side. That smear of mass across that 2D area results in this moment about the y-axis, this tendency to rotate about the y-axis. This looks a little strange because it looks like I have an x contribution and a y contribution in here. But I thought that moments about the y-axis were only due to the x coordinate. Well, remember where this came from. The x here is from the position. That's what's giving the, you're further to the right, so you want to rotate more. This and this came from the computation of the area multiplied by the density per unit area. So this f of x, this y contribution hitting the dx is actually what is giving us a sense of area. And this x here is what gives us the sense of the position. It's the analog of the statement up here that my is related to the x positions of the masses. This is the x position, this x that follows the rho and this before the f of x. The quote y contribution from explicitly seeing that f of x in there, oops, I hate when I undo and then it jumps all over the place, but this supposed y contribution from f of x is really just due to the fact that the height of the rectangle is needed to find its area and to find the amount of mass. So we kind of have this mass like rho f of x dx. Well, hey, that actually looks a lot like mass, right? This kind of mass, rho f of x dx, located at this position x. So it is concordant with what we've talked about before. It just, at the surface level, looks a little wonky. Okay, and then let's try to find the moment about the x-axis. So that is the tendency for this mass here, or this sheet, to rotate this direction about the x-axis. Well, that has to do with the y location, right? Remember? So mx sub I guess, the contribution to the moment about the x-axis, the tendency for it to rotate like up and down, due to this ith chunk, this roughly rectangle here. Well, that's going to be its y position, right? The y position of the center of mass. 1/2 of f of xy, f of xi, that's the y position for the center of mass, times the amount of mass at that position. What's that going to be? Well, again, that's going to be the area, f of xi, delta x, times the density per unit area. Mx, then, the overall moment about the x-axis, the overall tendency for this sheet, this smear of mass, to rotate about the x-axis is going to be approximately equal to sum I equals 1 to n, adding up all the influences of these little slices we've taken. We have 1/2 rho, so we got the 1/2 factor of the rho. The 1/2 comes from the fact that this location of this mass is only halfway up the rectangle. I have one f of xi from the y position, another f of xi from the height of the rectangle being related to the mass. So I actually have f of xi squared delta x. one of these guys, one of them is from the position, and one of these, this, and this is from the mass. And the position is also where that half comes from, because it's half of the way up the rectangle where the center of mass is. Again, we didn't see the 1/2 anywhere in the left to right, uh, or in my in the left to right center of mass, because we're saying this is approximate, especially as delta x goes to 0. The left endpoint or the right endpoint gets closer and closer together. But as delta x goes to 0, the top doesn't get closer to the bottom. So just to be clear why they look different and why we see the half here, but not in the other one, it's because as delta x goes to 0, the left and right endpoints get closer to 0. So that plus 1/2 delta x on the x coordinate just goes away. But the heights, as I squeeze in from the left and right side, the height is just going to stay about at f of xi. So we actually do need the 1/2 here. And then our usual trick. I don't know why my x is so far over there. There we go. N goes to infinity, delta x to 0, and mx becomes the integral from a to b of 1/2 rho f of x squared dx. This is the moment about the x-axis. This is the tendency for it to rotate vertically related to the y position. Moment about the x-axis related to y. So there are our formulas. And then, of course, x bar and y bar, the relationship between them, the moment and the mass, is exactly the same. X bar is my over m, and y bar is mx over m. So a couple notes. If the region's symmetric about a line of symmetry, so if I had a region, that was, say, a triangle like this, well, I notice that there's a line of symmetry here, this 45-degree line. This line y equals x. The center of mass has to line that line. So for instance, I'd know the y bar has to be x bar. Or if I had like a parabolic shape over a symmetric interval, doesn't look very much like a symmetric interval, but I would know that x bar has to be 0, and then y bar is whatever it is. But it's going to have to be on this line, the y-axis, because we're symmetric about the y-axis. So if I can find a line of symmetry, that can simplify my calculation significantly, right? Here I get x bar for free, essentially. Here, y bar equals x bar. I don't get either one for free, but I can choose which one I want to find, which one works the best for that function, find that one, and I get the other one for free. A second note, kind of a strange thing that's not just a mathematical curiosity, but is in real life. Note that the centroid is not necessarily within the area of consideration. It might not be possible to balance the mass, not just because of practical challenges of getting the thing in the right place, but for instance, take a washer, right? Well, if I were to look at this figure, which I think is called an annulus, if I remember right, mine's a little lopsided, but pretend it's nice and symmetric about the origin. If this is the region that I'm interested in, I see that I'm symmetric about the x-axis and about the y-axis, which I just drew opposite way than I said them. I see that x bar, y bar is the origin, the only point that lies on both axes. But that's actually not a point that can be supported under the mass itself. You can never balance a washer. I mean, and if you're thinking of it flat like this, I guess if you put it on its edge, you might be able to balance it. But if you're laying it flat like this, you can never, where you'd want to support it, there's a hole there. So the centroid is not necessarily within the area or the region or the mass, whatever you want to call it. It's not necessarily at a point that can be supported. Another note, kind of an interesting little thing, we can combine the ideas of discrete and continuous cases. I can imagine a discrete, or sorry, a continuous sheet like this with a discrete point mass. I don't know what I used up all my colors, but I can have a discrete point mass here, right? And I mean, I can basically think of the contribution to X bar from the sheet looking like this. These are different moments at different locations. I can find the center of mass of the sheet and a total mass there. And I could say that, well, on one hand, I have mass M, mass of the sheet, at location X bar, Y bar for the centroid of a sheet. And then I have another mass, call it little m tilde, some other little chunk of point mass that I put on here at location, X star, Y star. So the centroid of the sheet with the mass of the sheet located there, it can be treated like a point mass. And then I have another point mass. I'm just in the 2D discrete case. I have 2 point masses at 2 different locations. I can resolve the center of mass of those. If you've ever seen these little balancing bird toys, they look like they shouldn't balance because there's much more of their body and wings behind the balance point, and it's not just a perspective thing than in front. But I picked this picture because you can actually see, let me zoom in a little bit. It's just from Amazon. You can actually see at the very tip of its wing here, there's a darker section. There are little pieces of metal that have a much higher density than the plastic of the body. There are little chunks of metal that are in the tips of these wings. So if you didn't have those pieces of metal, your bird would definitely fall back towards the body because it's got more volume back there. But then you put a region of high density in front of its nose and it kind of balances right on its nose. Doesn't look like it should, but it does because of the higher mass up here. Or if you look at, another example from Amazon, these birds that are kind of like balancing on the Eiffel Tower. I think what's happening here, it's kind of hard to tell, but if you look at the one on the top right, it looks like the wings, it looks like they're very thin towards the back, right? It looks like the tails are pretty thin vertically. But if you look at the front of the wings, it looks like the whole thing is made of metal to me. I'm not 100% sure. If you look at the front of the wings closest to us, you can see they're actually thicker. So effectively making the density per unit area, if you punch to punch from the top to the bottom, the weight of the parts of the wing toward us are going to be heavier. It's going to be more weight, more mass there than if you punch the vertical punch through, say, the part of the wing further towards the back or maybe the tail or something like that. So the wings at the front are thicker, effectively changing the density per unit area from the back to the front. And we can make the bird balance, and again, in a way that it doesn't seem like it should at first glance. Okay, so we didn't quite get to this example. We might push this the next time, or um, I might write that example up as a supplement. But any questions on moments and center of mass from today? All right, let me stop the recording.